How does something as simple as a piece of wood going through another piece of wood take 6 months to figure out how to get to a finished product? Well, in this video, I'm going to be explaining to you how that happens and also hopefully justifying to myself the amount of time it's taken to get to this point. Now, just so you're aware, the video that you're currently watching, this one, is effectively an extended cut of a video that was posted on our main channel that documents this 6-month process of making a mallet, but condensed into 12 minutes. So if you've not got the patience for this video in particular, go and check out that one. But if you want to get into the weeds of why this took so long and hopefully learn a lot of things along the way, then this video will be for you. And I'll put some chapters in the timeline below so you can skip forward to relevant sections and maybe even refer back to them if there's something that you want to refer back to later. Now, just off the bat, before we get stuck into things, this video is primarily here for educational purposes because there will be a lot of information in here that will be helpful to people. And by sharing all that, I'm absolutely happy for people to just copy this design and make mallets of their own. It's hardly anything original. And so yeah, if you want to use the lessons and stuff that I share in this video to make your own, crack on. The only sort of boundary I would draw is don't go ahead and make copies and sell them. We rely on sales from these in order to fund the free content we do elsewhere on YouTube, such as the free online woodworking school, in addition to sharing videos like this where I can be fully transparent about all of the things we learnt about this. If we start getting knockoffs and stuff, it makes it hard to justify being this transparent about the process, which I really like doing. But you know, it's one of those difficult things. So if you want to make them for yourself, crack on, go for it. Just don't sell them. Thank you. Anyway, I've got all of my notes here, so let's get stuck in. So we start the process by selecting Leadwood blocks from our supplier Dalmann, who has a warehouse just up the road from us. Here we're looking for blocks that are both straight grained, dense, and don't have any sapwood or defects on them. Just so you're aware, this leadwood has been responsibly sourced from woodlands in Mozambique, details of which we'll put in the description below this video. And we'll also put the address of this warehouse you're currently seeing footage of in the description below if you fancy taking a look yourself. They've got such a good selection of wood sourced from Africa in that warehouse that it's well worth a look, and the staff there are also really nice and helpful. Once these are back in the workshop, we scrape the wax off the ends of them to determine the direction of the growth rings. We do this because wood tends to expand and contract more along its growth rings than it does across them like this. And so in the case of this block, it's going to shrink more in this direction along those growth rings than it is in this direction. The former one is referred to as tangential shrinkage. I never know if I'm saying that right. Tangential, who knows? So this is tangential. This is referred to as radial shrinkage. And so that's not to say that wood doesn't expand and contract in this direction, it just happens more so this way. We might as well address it. It doesn't really shrink this way at all. That's not worth worrying about. The reason I do this is because if this head wants to shrink, I want it to shrink into the handle and effectively make that mortise and tenon tighter. And so if we take a look at this head here, you can see that the growth rings are going across it like this. They're sort of quite obvious up here. And so if this moves, it's just going to shrink and clamp into that handle more. Whereas if that mortise were to be drilled on these faces and the handle was going through this way, now most of the movement in this head is going to be happening up and down the handle. And over time, it could end up weakening that epoxy joint. And just so you're aware, ignore both of the state of these components. They are prototypes. So we've got a few over here that are pretty much ready to go, and as you can see, the growth rings are pretty much always going across the faces like that. And the added advantage of this is it also gives you sort of linear grain on the faces rather than this through sawn look that you can see on the top faces that, you know, it still looks kind of cool, but I much prefer those kind of lines that you get from the way the sort of quarter sawn grain interacts with it. So once the direction of the growth rings has been identified on these leadwood blocks, that will dictate which face we drill into to create the mortise for the tenon to go into. And to do that, we place it onto my pillar drill with a 30mm sawtooth bit. Sometimes these blocks have small variations in widths, meaning I have to adjust the fence to get true center on each one. But in the future, I'm probably just going to go ahead and put them all through the thicknesser before doing this step, just to make sure they're all the same consistent width. Because if I don't pay attention to getting it bang on true center at this stage, you start ending up with mallets like this where the handle doesn't intersect the head in a sort of symmetrical way. And in terms of life of this drill bit, I've found it can drill roughly about 50 holes in the leadwood before it just sort of becomes a bit knackered. Now, one thing you might have noticed in the video is some of the blocks have 3 holes in them for the mortices, whereas others only have 2. Previously, we were able to fit 3 heads into a block because the prototype mallets that we were originally prototyping had a concave face on them rather than 2 convex ones like you see on these final mallets. This concave face allowed me to squeeze more out of the material because there wasn't a bump to account for on both of the faces, but due to the fact they were slightly harder to manufacture than the convex faces and at very little and, to be honest, somewhat unproven benefit, we decided to just go for the convex face on both sides of the mallet. Unfortunately, the knock-on effect of this is by having to account for those 2 bumps, we don't quite have enough material to squeeze 3 heads out of the block, because by the time the prongs from the lathe have stuck into the end grain and we've sliced this up and the kerf of the bandsaw and everything, it's just not quite enough to squeeze out. But fortunately, we're able to save that sort of leftover section to make into a future tool that we're going to be developing soon. And so while the corners are still attached, we'll find the center of the block by marking across the diagonals before then slicing them off using this bandsaw jig. This works by referencing in the mitre slot of the bandsaw, providing the perfect distance from the blade when the bed is tilted to 45 degrees. I'm considering remaking this into a jig that works while the table just remains flat, both to avoid the faff of having to tilt it to 45 degrees and then set it back to square when I want to cut something at 90 degrees. And additionally, the one that I'm currently using that slots into the mitre saw track does tilt ever so slightly, and it's just probably not as safe as it could be. My jig. And so at some point I'm going to end up fixing that. But this jig was made quite early in the process of developing the mallets. However, we were quite frequently having this issue with slicing off the corners where the heads would end up sort of in weird shapes and things like that, that when put on the lathe would be severely unbalanced and potentially unsafe. And it took me a while to figure out what the actual issue was here, but I did eventually figure it out. Essentially, what I was doing on the first few blocks was simply rolling them clockwise or anti-clockwise after every pass. The issue with this is, as I just mentioned, the Leadwood blocks are not always perfectly square, and by square I mean both in terms of actually being square shaped and also square in terms of 90 degrees. They can be a bit all over the place. And so if you take a rectangular shape and roll it through the bandsaw like this, you end up with quite a weird shaped section that, when compounded with the block being out of square, can cause quite severe imbalances when on the lathe. And so the fix that I eventually figured out was to make sure that the mortise holes were always pointed in the same direction as it was going through the corner slicing jig. This is kind of the same as using face sides and edges when you're machining or using hand tools on timber, but also not quite the same because you're using different. It's just making sure that the holes are always pointed in the same way. So you can see there, instead of flipping the piece 90 degrees, I turn it a full 180 degrees end to end to give me access to the 2 remaining corners of the block while still having the holes pointing to the top right. And so here's what we're left with after cutting the block correctly. But if we flip this round 180 degrees and see what we would have cut had we just rolled it, you can see that the 2 opposing corners would have been cut much deeper than what we're currently seeing. Anyway, the Leadwood block is now ready for turning. We've got the corners sliced off, we've got the center marks done, and we've also drilled some small holes in the center just to help the prong drives from the lathe dig in as much as they need to.
It did sink into it. Barely.
But before taking the Leadwood to the lathe, we're going to have a look at the olive wood handles, because these things we had an absolute nightmare with, and is probably what 60 to 70% of the delays we experienced over the 6 months have been down to. The main one being issues with concentricity of this coin in the top, which we just couldn't pin down what the issue was. Well, that's definitely not central. And so the first step in making these olive wood handles is to drill an 8mm hole into the end grain with a 20mm counterbore surrounding it. The function of this hole is twofold. Firstly, the 8mm hole provides a point in which I can screw onto my lathe at a later stage to give me full access to the handle when sanding it down to its finished diameter. This means I don't have to use any prong drives that might damage the material and create extra work to try and remove later. The counterbore above it is to accommodate the coin, which both brands the mallet and gives me a point that I can put the logo on it, while also hiding that mounting point below that I was using to sand the handle. Now, we're only focusing on the drilling part of this coin at the moment, but just to foreshadow something that happens later on, the coin itself became a huge issue later in the process that I'll obviously document a bit later on.
Back to the drawing board.
Yeah.
We'll give you an update when we got some answers.
So the original idea here was to pre-drill these 2 holes while the block was unturned, then machine up an adapter that we could use to mount it on the CNC lathe to achieve perfect concentricity. And so let me talk you through all of the difficulties we faced trying to make this work. The first issue that we faced was that we couldn't get hold of the counterbore required to clamp to the outside of the 8mm drill bit, because it was on a 6 to 8 week delivery time from Switzerland. And so while prototyping these mallets, I was drilling the holes in 2 separate processes. The first method I tried was making a 20mm hole using the pillar drill jig, then used an adapter bushing to locate an 8mm hole in the middle of this hole and drill the mounting point for the screw chuck. However, this bushing didn't quite have enough location to be accurate enough and kept giving me holes that weren't plumb. And so as a result, I resorted to carrying out both processes separately on the pillar drill. First, I drilled the 20mm hole in all of the blocks, then without moving the bed, swapped it out for an 8mm drill bit and drilled all of the blocks again. However, this then causes another issue to arise, which is the variation in the dimension of the olive wood blocks themselves. Because like the Leadwood, these were not always perfectly square, both in terms of shape and squareness. Some of them were twisted all over the place, and yeah, they were a nightmare. So when I was doing this, I had to ensure I kept the same 2 edges pressed against the fence while drilling it, which was basically like using a face side and a face edge. Because if I ended up accidentally rotating the block and referencing the wrong face against the fence, the 2 holes would end up being misaligned and we would have more issues. So this could normally be fixed by simply marking the face side and face edge marks that I just mentioned. However, as I just kind of said, these blocks were rarely cut straight and they quite often had bows and bends and stuff in them that even if you reference the same 2 edges against the fence of the pillar drill, they could still rock all over the place. And so the only fix I could come up for this was adding the process of planing the face side and face edge onto the blocks prior to drilling, using my planer. This did seem a bit pointless in some ways, because planing a flat and square edge onto a block that's just going to get turned away later on is like, why are we needing to do this? This is such a bad waste of time. But at the same time, like, what can I do about it? The blocks were going to rock on the pillar drill jig if I didn't do this. But unfortunately, after a few tests, even with this convoluted process of planing all the face sides and edges, cutting the blocks in 2, drilling the 20mm hole in the blocks and switching it out for an 8mm bit before repeating the process again, we still had concentricity issues. Still, even after making multiple adapters to really fine tolerances that were fitting the lathe and the block perfectly, nothing was working.
What's going on? Is that wonky already?
Well, yeah, going in wonky there.
So then we took a step back. We took a look at the pillar drill and we realized that, that might also not be drilling perfectly plumb. Maybe the bed needs to be trammed in relation to the head of the pillar drill. So I went out, I bought a pillar drill tramming jig that I think also works for milling machines. I'll put a link to it in the description below if you're interested. And I also remade the drilling jig to be more secure and have a more adjustable back fence so I could really dial in how perpendicular the block was to the drill. And the adjustable fences on this pillar drill jig are actually quite easy to make. You simply have a threaded insert on the back wall and a thin countersunk bolt nested into another sheet in front of it. This setup alone will allow you to move the fence inwards, but it won't allow you to move it back. There's a couple of ways you could go about this. The first is to put a spring on the back which will keep tension pushing behind the thread, thus allowing the fence to come forward when the bolt is loosened. The issue with this is that I'm going to be pressing against this fence with the block and the spring will be too spongy to provide a secure backstop for it. And so the method I chose to use was to glue another cover over the countersunk bolt, which would then make them captive between the 2 layers, but making sure to have an access hole drilled into the outer skin which would still let me adjust the bolt from the front. And so with this setup, now if I tighten the countersink bolt, it pushes on the back wall and brings it into the fence, and if I loosen it, the top of the countersunk bolt pushes on the front fence and pulls it away from the back wall. Genius, eh? And it worked really, really well and was super satisfying to use and really dial in. And so, with all of these added steps, just to reiterate, planing the face sides and edges, cutting the blocks in half, making sure to reference those face sides and edges against the miter saw, drilling them on the pillar drill and using a jig that I know is bang on 90 degrees, both because the bed is trammed to the pillar drill from above and the fence itself has been adjusted to be spot on. We were still having concentricity issues. I mean, the pass rate maybe increased to like 50%, but like, it was still an issue. We couldn't fix it. Now, we've all had this before where the fix to your problems is right there in front of your eyes. You know what you need to do, but you're so invested in the process that you've already taken that you're sort of reluctant to let it go and you just want to fix it. But before I show you this fix that was right in front of our eyes the entire time, we need to move on to the CNC lathe because that will give context as to how this fix actually worked. So I purchased this CNC lathe sometime around the middle of 2022, and by the time it was delivered in November later that year, it sat unused in this workshop for about 14 months, just haunting me at both the financial expense it took to get it here in the first place, and also the investment in time I would need to take in order to learn how to use it. The machine itself is from Style CNC, who are based out in China, and to be fully transparent, it cost me about £6,000 to purchase, plus another £2,000 to get it onto the ship, imported to the UK, and then transported to my workshop. Then another large sum of money on top of that in order to get it wired into a 3-phase circuit board into my electrical thing, whatever it is. I should know this by now, I'm converting a bloody van. And so as you saw in the video, the manual was very basic and seemed to assume a lot of prior knowledge. We don't even have a miller on it.
No. No, it sort of applies to multiple machines.
Plus, as you'd expect, a lot of the important information was just lost in translation.
Welcome to use this system.
Right. Where was that dial handwheel thing?
It's all in Chinese.
It's all in Chinese.
And so we had to figure things out both through trial and error and messaging the engineers directly to try and get answers to some of the issues we were facing. And to be fair to them, you can't knock their customer service. They were very, very helpful. So this lathe has got a dual spindle on it for turning 2 things at once, and it's got 2 knives per spindle, one of which acts as a kind of roughing cut and the other acts as a smoothing cut. And then on the tailstock, it's hooked up to our air compressor, which keeps constant pressure on the piece while it's turning. Oh my Lord. Okay. Now, what's funny is in this instruction manual, there was absolutely no mention of this airline whatsoever. And to be honest, we had no idea what it was when we saw the machine.
How can we do this in the safest way possible?
Also a regulator, maybe? I don't know how these work.
It seems obvious now, and I was kind of thinking it might be some sort of air compressor, but I didn't want to just plug an air compressor into it and pressurize the whole thing, not knowing if that was what I should be doing or not. And so as a result, the first few tests that you saw us running in that main video where the pieces were vibrating, we weren't actually using any air pressure whatsoever. That was just us ramming the tailstock into it, locking it into position, and then just hoping for the best, which is what caused that horrible vibrating noise that you heard in the test program that we were running.
Oh dear. Oh dear.
By the way, that sort of spindle that you saw it turning, that was a test program that came with the lathe that you can use to basically zero the cutters and make sure everything's working correctly.
That was so good.
I tell you what, for a shitty bit of wood like this, that is a really good finish. As I also mentioned in the overview video, we also managed to install this machine backwards in the room.
We just discovered something.
Every video they sent me, it was on this side.
And that's why the handles are on that side as well.
Because I just assumed that headstocks on lathes are normally on the left-hand side of the machine, and so why would this CNC lathe be any different? Well, it turns out it is, for some reason.
Can I have the oil, please?
I'm never getting out of this.
Oil.
Okay, maybe there is a good reason for it, but we've literally built a room around this thing now, and we can't move it. We're just gonna have to work with it as it is, which isn't ideal. And so with this lathe, let's take a look at how the Leadwood heads are made. The prong drive on this lathe has a massive spike on the end of it, probably twice as big as what you'd find on a normal woodworking lathe. And due to this large spike, the air pressure was not strong enough to allow the teeth to engage in the grain. And so we needed to drill a small pilot hole in the end grain to allow them to actually bite in and engage.
Okay, that went in. That didn't go in at all.
This pilot hole, in addition to the convex faces on the mallets and the small spike left over from the tailstock, is the difference between being able to fit 3 heads into one of these Leadwood blocks as opposed to 2. And so it's a shame we couldn't quite get the yield we wanted, but as I said before, we can use those blocks for something else later on. But the Leadwood heads are pretty straightforward. It's just a straight pass all the way through. A little bit scary having something that heavy spinning at that many RPMs on the lathe right in front of you, but it's a pretty simple process, and by the time the corners are sliced off, the cut isn't actually that heavy. And so next we'll talk about the designs for the handles, the various iterations we went through in order to get to something that fits this well. But before doing that, I'll just go off on a small tangent and show how the drawings for these handles are actually made and how the CNC lathe interprets them. So making drawings for the lathe is quite simple, and I make them on AutoCAD. In a nutshell, I create a turning of the unturned olive wood block at its widest point, and then overlay an outline of the turned handle into it. Next, I need to figure out a path for the cutter to follow. In the case of this handle, it's pretty much all there, other than an exit cut which I can add at the top here. I then add dimensions to this and print it off as a drawing that we can use to help kind of zero the cutters when it comes to using the CNC lathe. I've got drawings this time.
Oh, very nice.
This reflects the size of the wood that's in it.
Okay.
And it'll show how far out you need to set the 0 point from the center point, and then how far back as well you need to do it. And then in order to make it into something that the CNC lathe can actually read, I'll turn it into a simple line that's simply done by removing half of the drawing while maintaining the in and out points. Perhaps more importantly, the start of the line needs to be zeroed within the AutoCAD program by placing it on the coordinates 0, 0, 0, and then it's exported as a DXF file onto a little memory stick and then plugged into the lathe. Now, I won't go into too much detail as to how the CNC lathe is set up because it's very bespoke to that lathe. It's very confusing, and to be honest, it's more Rob's realm of expertise by this point rather than mine, and me trying to explain it would be useless. But in a nutshell, once the number of passes and the RPM and the cutting speed has been dialed in, we just need to figure out the 0 point for where the cutter needs to start. And so inevitably there's a little bit of trial and error trying to dial in this offset for the 0 point, but once we've got it bang on, we can note down the machine coordinates and easily return to them later on without needing to test every single time the machine is set up. And this is what allowed us to get results like this pretty much every time. Feels like 30.5.
30.5, yeah?
Oh, fucking hell.
Oh, what?
Witness. So I mentioned that this handle went through multiple design iterations before settling on the final design that we've got here. So starting off with this one, this is just a simple straight spindle that is sanded to fit a hole in the mallet head. The difficulty with this is getting a consistent diameter down the entire length of this tenon and have it properly engage in the mortise up the entire length of it. And it turns out this is incredibly difficult to do with sandpaper. Obviously we machine these to 30.5 off the lathe, and then I try and sand away 0.5 millimeter to get it to fit that 30 millimeter hole. So the first method I tried was to simply sand it and then just constantly measure it with calipers to try and hit all the points that were still slightly over 30 millimeters. But just saying that, you can probably understand that this took an incredibly long time to do per handle, and to be honest, wasn't even that accurate. It was so easy to try and hit a certain area with the sandpaper and then accidentally hit the wrong area, take that too low, and then you've got a loose wobbly spot on one of these things. So then next I made an adapter to fit onto the screw chuck, which would let me measure the diameter of the spindle as I was turning it. This did make slight improvements to both the time and the accuracy when producing this straight tenon, but as the ring I was using to measure this diameter got used more, it obviously wore down over time, and then it just made it inaccurate. And so while I still didn't quite have a fix for sanding this down to the consistent diameter I needed, version 2 of the handle included these very small grooves going up the length of it, because one thing I found with these, and this handle kind of attests to this, is it's very hard to get epoxy to stay on the handle when you're squeezing it into the mallet head. I'll sort of detail this a little bit later on, but version 2 includes these very small reservoirs that just give the glue a bit of extra area to gather and pull in and help sort of carry it into the mortise of the head a little bit better. And so this definitely increased the strength of some of the prototypes, but as I said, it still didn't quite address this issue of sanding down to the 30 millimeter diameter that I required. And then eventually on one sleepless night, and honestly, these things did keep me up at night, just racking my brains trying to figure out how I was going to do this, let alone all the other stages we had to figure out. One night, I came up with a plan as to how we could fix this. You see, currently, this handle with its grooves and everything is being turned to 30.5 millimeters in diameter and then sanded down to 30 all the way along. But this part of the tenon in the middle where the grooves are is never seen. And so why do I need to sand this middle bit? It's only this bit here and this bit here that need to be sanded to that sort of 240 grit finish that I'm looking for. I don't need to do anything in the middle. And so what if I program the CNC to turn this top section to 30.5 and this bottom section to 30.5, but this bit in the middle, just bang on 30. Simple. And it turned out This worked brilliantly. Not only would it massively decrease the amount of sanding needed in order to get these to the state required, but it would allow me to be so much more accurate at the 2 points that I needed it to be tight, that I could achieve a really tight and consistent fit with these handles. And so this was the fix for version 3 of the handle, which massively increased the speed and the accuracy and the consistency of everything. And after sanding everything to 240 grit and parting away the excess material on the bottom, gave me a really, really nice looking handle that was all prepped and ready for pre-finishing before assembling it. But before we do any of that, let's go and take a look at the Leadwood again. So this is how the blocks come off the CNC lathe, and the finish is very nice. It's surprisingly good.
Oh.
Thank you, mate. Well, that's a rather nice finish. That is so...
Bloody hell.
But of course, we want to take them a step further and make sure those are sanded to 240 grit as well. And so I do this by mounting them onto my normal wood turning lathe. And for this, I purchased these incredibly helpful centers called Pro Drives, which are manufactured by Axminster and have an adjustable spring in the middle. This allows them to be tensioned to suit materials of varying hardnesses, which is helpful for Leadwood because my normal prong drive was not sharp enough to embed itself into the end grain. This Leadwood is then sanded all the way up to 240 grit, being very careful not to get my fingers caught in the holes as they spin. Honestly, if you're doing anything akin to this, watch out for that. That is an awful accident just waiting to happen. Make sure you're using a sanding block and you're not pressing too hard with it so that if it slips out, your finger goes into one of the holes while it's spinning. This is your warning. Don't let that happen to you. And so once it's all been sanded and the lathe is turned off, I can then finish by sanding with the grain to make sure we get rid of any cross grain scratches. These can then be taken over to the bandsaw to be sliced into 3, which is done so using this jig. It uses very much the same idea as the corner slicing jig by locating in the miter saw track of the table, and it puts the head in a position that cuts perfectly halfway between the 2 mortices.
Oh, yes.
That's quite precise, isn't it?
That's a bit of veneer.
That's nuts.
That's really satisfying.
Yeah. Wow. Additionally, the cradle shape of the jig and the fact that it locates on the tenon also prevents this thing from spinning when the bandsaw blade engages with it, which is something that bandsaws are notorious for doing when you're cutting round material. So with these blocks now sliced into head blanks, next, the faces on them need to be domed. Now, when I made these mallets in the past, and I'm talking all the way back in the Turning Tuesday series I used to run in my old workshop. Damn it! I hate the skew! I did this with a scraper, but as you'd imagine, this is both a very slow and inconsistent process. And in addition to this, it was also very difficult to figure out a way of holding the heads which would prevent any damage from them. Because remember, the outsides of these have just been sanded to 240 grit. If I'm using a jaw that clamps down on those in order to hold it while I'm shaping that incredibly hard end grain, that's going to leave some sort of teeth marks in it that's going to be difficult to remove later. For example, Axminster, the manufacturer of the chuck that I use, designed these jaws called gripper jaws that would definitely have the grip required, but would clearly leave indents in the freshly sanded perimeter of the mallets. And so I was left with no choice but to make my own jaws using these wood jaw plates that were also produced by Axminster. And these basically just mean that you can attach whatever you want to the face of this to hold whatever you want. Now, I've never made jaws like this before, and while the first ones somewhat worked, the fact I drilled and assembled them prior to attaching them to the chuck caused all sorts of concentricity issues as well as looseness around the outside of the head, which meant the mallet head was not held quite as securely as it could have been.
Oh boy.
Ugh. The result of this being some pretty bad catches as soon as a scraper is involved.
Oh! Oh no. Whoa!
And think about it. If these jaws weren't going to work with the scraper, there was no chance of them working with the router jig that I'd planned to make that you'll see in a minute. So with this second set of jaws, I attached the plywood blanks to the lathe and drilled out the center with a 3-inch hole saw while it was spinning on the lathe.
That looks better, actually.
Yeah. The reason I didn't do this before was because it just felt somewhat unsafe doing that. And I tend to follow that kind of idea that if a process makes you feel uneasy, don't do it. But in reality, there was no other way of doing this, and so I had to just sort of bite the bullet and do it. And it turned out that it was actually quite an easy and smooth process, and apart from anything, it massively improved the accuracy and the grippiness of the jaws. And so with those made, next we can turn our attention to the router jig that I'm going to be using to dome the faces of the mallets. And so after carefully measuring the key dimensions on my lathe, I designed this router jig on AutoCAD before getting templates for each component cut out on our CO2 laser. These could then be glued together and flush trimmed where necessary, and then assembled into a tower that clamps my unused palm router at the perfect height for the lathe. Now, it would be irresponsible of me to promote this lathe jig as a good idea or a lathe hack. It's not. No, there's no way that is coming out. I can't even like twist it in there.
This is far more precise than I expected you to be.
It's definitely not something I suggest on making, and you know, definitely don't consider using this as a way of like mass producing bowl blanks or something like that. Bowl gouges exist for a reason. Always use the correct tool for the correct process. It just so happens that with doming these faces, I literally couldn't figure out any other way of cutting that accurately and consistently. And so as you saw in the main video, it took me a while to get to grips with the feed directions required to make this actually work. And in reality, I actually got quite lucky with this because I didn't put any forethought into it whatsoever. I just turned the lathe on, turned the router on, and started feeding it into it. Fortunately, on the first pass, it was that example I gave where the cutters meshed together like gears. And although it did kind of cut, it was just sort of very horrible and vibraty, and it didn't give the finish I was looking for. If I got this wrong and I had the lathe in reverse and I fed the router into it and it caught, that example I gave where it could fly across the room could have actually happened and I wouldn't have been prepared for it. When it comes to routers and lathes, always consider the feed directions and the rotation directions of the things you're using, and think about where the pressure is going to be applied and prepare for catches. Thought you all might appreciate this, so I've sort of shown it a few times. I'm using this router jig to slightly dome the faces of these, and I just had my first catch with it. You ready? It's safe to say my trousers are not the same colour. You know, this is a bit of a self-confessed slap on the wrist for myself. I should have thought about it. I got really lucky. Unfortunately, I just so happened to think about it prior to making the wrong move. And so in addition to figuring out the speed and technique I wanted to use when using the router jig on these faces, the other thing I wanted to experiment with was using different cutters and the finish they would create. So the router jig was originally designed to fit a 1/2 inch round nose cutter, which is what the guide on the bottom of the jig is kind of outlined to match. I chose this cutter because in theory, the sort of rounded edge of it would ease the cutter into the edge of the block and hopefully minimize the breakout. But what I found was the smaller diameter of the round nose cutter combined with the fact that the palm router has one fixed speed on it just meant that I wasn't quite able to get the cutting speeds I required to make it work and get the finish I required. So I got a larger round nose cutter on order, and in the meantime started experimenting with straight cutters to see how that would work instead. As I kind of predicted, this was much easier to feed into the material, but it came at the massive expense of huge amounts of breakout around the perimeter of the faces. And so I eventually received the larger round nose cutter and put it to work. And this increased cutting speed definitely worked, but I was still getting issues with small bits of breakout around the edges of the mallet that I wasn't quite able to remove even after sanding the faces and putting a heavy chamfer around the edge of it. And so after a little bit of head scratching, I realized that heavily scoring the edge grain before shaping the end grain would dramatically improve the finish of the edges, as any of the pieces of leadwood that wanted to chip away would prematurely be severed and they wouldn't be able to travel any further down the head of the mallet. So I made this thing, which is a stick of wood with 2 marking knife ferrules stacked inside of it. I don't need much of the blade poking through, and so this second one on top is purely there to help rigidify the blade. And in addition to this, the blade is offset 10mm from the edge of the handle, which helps me line up where the perimeter is going to be scored. The only thing I'm lacking at this point is a line to show me where it actually needs to be scored. And so for that I made this thingy, which registers into the mortise and gives me a perfectly symmetrical distance from the center of the head to either face. I can then trace around it to mark the size of the head, which then goes into the chuck, measuring a distance of 10mm from the jaws to match the 10mm offset from the edge of the tool to the blade. And then I can reference the edge of the scoring tool against the faces of the jaws while the lathe is spinning in reverse and score that line exactly where I need it. And this was an instant fix to all of the breakout issues I was facing. And in addition to that, it massively sped up the process because now the head was protruding the same distance from the chuck every time rather than me just eyeballing it every time I went to do this process. And the router jig base is fixed into the lathe bed, and so I don't have to go ahead and like trial and error with that and everything. Everything screws into the exact same position as it was previously, and I can just get to work routing the faces of the mallets. So with the faces domed, next the faces can be sanded to 240 grit. Nothing too special about this other than taking the time to add the chamfers with sandpaper and then finish up by sanding in the same direction as the end grain growth rings to prevent any circular scratches from appearing. I then scrub the insides of the mortise with some methylated spirit, which will both aid the glue bond and get rid of any residual dust that may end up mixing with the epoxy and stain the grain of the olive wood as it's pushed through. And speaking of olive wood, here's Rob explaining how we managed to fix the concentricity on the handles.
Shut up! Oh. But this is where you saw us having the problems way back when. It's had a few additions. These are some laser cut parts that basically hold a handle in place because we've reordered how the handles are produced. So let's go in order. Obviously, we start with a block. We cut the corners off as you've seen in previous videos, and then we take the block, hello, to the lathe. So this solid block without any holes pre-drilled gets slotted in here, turned using the program that we've established before, and we end up with something like this. This is an early prototype, hence the flat spots, and it's this without a hole in the top, ignore that we then take to the pillar drill. The pillar drill, now with its laser cut components, can create a perfectly concentric circle in the top.
And with that simple reorder of the processes, all of our issues with concentricity were increased from a 50% success rate to 100. So now with the handles and the heads prepped, I could pre-finish them with Osmo. Now there's a couple of reasons why I'm pre-finishing these prior to assembly. The first reason is that the hard wax oil I'm using will help prevent the epoxy from soaking into the grain of the handle, because this will produce staining, it will make it hard to remove later, and just having that protective coat provided by the hard wax oil will just help with that epoxy removal later on. The second reason is I've had that bucket for ages and I just need to use it up. Of course, when I'm wiping away all of the epoxy squeeze out with acetone, I usually end up wiping away the pre-finish anyway, but it's already kind of served its purpose by that point by preventing the epoxy from soaking in, and so if it wipes away, I can just top it up later. So next we are going to talk about gluing the mallets, and this is a real pain in the arse. In the first run of mallets, I hadn't quite figured out my sanding technique to get the perfect diameter and the perfect fit between the handle and the head. And so while it was a kind of acceptable fit, there wasn't quite enough friction to hold it in place while the glue was sort of in there. This meant that while I was wiping away the epoxy on one side, the head would be sliding down, and so I'd need to wipe it away, and then if I wiped the opposite side it would move up, and then it was just moving all over the place, and I was having to go constantly back and forth wiping away all of this epoxy. Additionally, I found that I needed to absolutely flood them with epoxy in order to get the correct amount of coverage within the mortise and tenon. Because if I just apply epoxy to the tenon, by the time I push it into the mortise from below, it all squishes out the bottom. Whereas if I put epoxy into the mortise and not the tenon, when I push the tenon into the mortise, all of it squeezes out the top. And so the reservoirs in the handle like somewhat help this, but what I found is that I needed to just put epoxy on both this and the mortise in order to get the coverage I required, which means tons of squeeze out to clear up afterwards, but it does mean that it's definitely got full coverage in there. And in addition to the friction that I'm able to produce on these things now, I can get a really, really secure fit. But this experience of trying to glue these somewhat loose handles into the head is what prompted me to make the gluing jigs, which both give me the perfect protrusion from the top of the leadwood and allow me to fully access either end of the mortise and tenon to wipe away the excess epoxy. These jigs, in combination with a much better fitting tenon across the board, has made this stage much more manageable. I just wipe away as much excess as I possibly can with the jig in position, then I sort of wait for 6 to 8 hours for the epoxy to gel up, remove the jig, and then I've got even better access to the rest of the head so that I can wipe away any leftover epoxy while it's still kind of tacky enough to hold the head in position while I do all of the cleaning. So the mallets are now glued up. Next, we can look at the coins. So originally we had these outsourced, but due to the supplier being very busy, we found ourselves on yet another 6 to 8 week wait list. And so while we were waiting for these to be made, we used the laser pecker to prototype the design, which really helped us figure out a lot of processes prior to getting the final coins delivered. Well, that looks terrible. However, unfortunately, Once we received the coins after such a long wait, the tolerances were just not there due to errors both in the manufacturing process and the communication.
Deep enough, yeah.
I was going to say, is it a different size though? It's a different size of coin head.
Are they?
I thought it was.
I hope so.
Because that seems really small.
That is quite small.
Sorry, I'm not getting a shot at that again. Okay, there's a different size, Wait, where are the calipers?
Let's get the calipers. No!
That's minus a lot more.
Yeah.
Than 0.05.
Fuck.
This is not good.
Yeah, they're all like that. Well, that is a predicament.
If I'm honest, it wasn't really anyone's fault. I can definitely see where they went wrong with it, and I wasn't angry with them. It was just like, of course this happened. And to be fair to them, they owned it. They gave me a full refund. I've still got the defect coins here somewhere. They just said toss them or whatever. Like, honestly, they handled it really well. It was such a shame that it took so long, and this was like the final step we had to figure out, and it was just going to cause us more delays. And so with this kind of revelation of the coins that were not going to work, we were left with no other option but to also produce the coins in-house. And for that, we reached out to a company called CloudRay for help. Now, CloudRay manufacture these things called fibre lasers, which are among some of the most powerful laser engravers you can buy and are capable of vaporizing metal much faster and deeper than the more consumer level lasers that we've been using up until now and you commonly see in sort of maker spaces and things. It is a bit of an investment in terms of cost, but as far as we're concerned, nothing else can do the job as well as one of these things, and it gives us the security we need to produce these coins, as well as the potential to create a variety of other future projects entirely in-house to the tolerances and the quality we require. I'll put a link to this specific machine in the description below if you're interested. As I said, it is a bit of an investment. It was provided to us for free as a kind of sponsorship deal, but there is nothing else compares to it. If you want to engrave metal with a laser, this is what you need.
Remember, this is what we originally produced for the prototypes, and they just don't have the depth that we needed. They are really good for testing the concept, but we needed to go further. That's where this lovely thing engraves it into turning into something like this. Now, this looks pretty poor, and I think this one's off center. This must have been an early one, but once you polish it up, you get something like this.
And so up until this point, I've been machining the coins on my manual lathe. These are turned down to be fractionally larger than the diameter of the hole in the top of the handle to give it a much better grab, as well as having a small chamfer filed onto the bottom to give it a good leading edge as it's being set into the handle. Eventually, I'll outsource these coins to the same company that manufactures my marking knife ferrules for me. But for the time being, where we're still working with small quantities like this, I might as well just continue doing it in-house, because apart from anything, it gives me a bit of practice in using that machine properly. And so once the coins have been machined, I quickly clean them up with a bit of sandpaper, and then they go into the fibre laser, which engraves the design onto the face of the coin using a piece of software called Lightburn. Rob then takes these to the polisher to get them all cleaned up before handing them to me to be set into the mallet handles. The only thing I need to keep an eye out for at this stage is the epoxy squeezing out the sides of the coin as it cures, because when we push them in, we are compressing air underneath. It's that tight of a fit, and that air is going to want to escape, and it's going to be pushing epoxy out with it. And so in some of the early runs I did, this is something that happened that I wasn't prepared for. I came back the next morning to find a bunch of mallets, all with loads of epoxy squeeze out on the outside of them, which in theory could be cleaned away, but that would obviously damage the coin. It would stain the wood around it. And even once the epoxy was cleaned away, it still left tarnishing on the coin. So now what I do is when the coins are in there, I leave them in the gap of my workbench like this, and I just come back every sort of half hour or so and just wipe away any epoxy that squeezes out until no more epoxy squeezes out. And so with everything now dry and glued in position, next we can start applying the layers of finish to the mallet. So I'm going to apply 2 layers of hard wax oil to these, but before doing so, I'm going to give everything a quick scrub down with some fine abrasive pads to get rid of any sort of grubby finger marks that have been picked up along the way. And that is how you end up with the finished mallet. But we're not done yet. because we still got packaging to figure out. Now, one of the things I am really picky about is making sure that our packaging is consistent across the board, both in terms of the sort of quality and the looks of it. We wanted something that would both present it to the customer in an attractive way once the lid was opened, and also keep it nice and secure in transit. We had the option to use foam for this in a similar way to what we do for the knives, but we decided to use cardboard to properly support the mallet from underneath. Again, this packaging was designed entirely in-house on AutoCAD, which was pretty easy to do considering I already had the outlines of the head and the handle ready to go. And by this point we were sort of looking at what we had and we were like, we've got a finished mallet, we can produce all of the packaging in-house. Why can't we just, why do we have to outsource the packaging? We could just do it all here. Well, that's what we thought until we went to put a perfectly finished mallet into the cardboard that we just cut out on the laser cutter, stood back and admired how beautiful it fit, took the mallet out and then noticed all of this black staining around the edge of it due to the burnt edge of the cardboard. Now this can somewhat be removed, but a lot of the time by trying to remove it, you just end up wiping the charcoal further into the grain and staining it more. And we tried fixing it using various means, such as brushing away the burnt edge of the cardboard and sealing it under a layer of shellac sanding sealer. But the added time and effort and fumes associated with doing so, it made us realize this isn't worth doing. We do need to outsource this. Now we work with this brilliant company just down the road from us called the Marketing Production Company. And they're the ones who manufacture all of our packaging for us to the specifications and budgets we ask for. What's better, while they do have the capability to design packaging for us, as they did with my marking knives, in this case, we'd already gone ahead and produced the DXF templates to produce on our laser cutter that we could just hand across to them and get them to cut out on their, I think it's called a plotting cutter. It basically cuts with a knife rather than a laser, which obviously means you're going to be left with an edge that is cut very cleanly, yet doesn't stain the wood. Additionally, to keep the branding nice and cohesive across the range of tools we are currently offering and will be offering in the future, we ordered sleeves from them in the same black soft touch material that if you've had one of our marking knives, you know how nice that feels to touch. We also covered the cardboard on the inside of the box with a layer of foam, which matches the exact same aesthetic as the marking knife, so that looks consistent as well. And then we've also got some foam to go in the lid of the box to help keep the mallet pressed down into the sort of nest below while it's in transit. And so with all of that, that's how the mallet took 6 months to produce. Tons and tons of trial and error, both in manufacturing the mallet and all the processes that were required to make this thing, figuring out how to program a CNC lathe that came with a horrible instruction manual, dealing with delays from suppliers, dealing with outsourced components that weren't up to the quality and tolerances we required, and not to mention all of the other things that just happen to distract you along the way that comes with running a business, I guess. It was not an easy process whatsoever, but we're finally there, and at the time of filming this video, they're currently available to pre-order. However, if you're watching this much later on, you might just be able to go to our website now and buy them using the links in the description below. Now, as I said at the start of the video, we have covered a lot of things in this. There's a lot of pointers that hopefully you could use if you want to produce something like this yourself. But as I said, just to reiterate, please don't go ahead and make copies of these and sell them. We rely on sales of these in order to fund the free content that we have in order to share woodworking expertise with the wider world. It's just something that I ask of you to respect, I guess. So with all that said, if you're interested in getting one of these things, everything is linked in the description below. I'll also put links to sort of the various tools and the jigs and consumables that we've used throughout this process below, if you're interested in any of them. And if you've got anything you want to ask us about this mallet, either leave them in the comments below or just contact us via our contact page on the website. There's also a link for that in the description. Thank you very much for watching. Thanks for bearing with me. I'll see you in the next one.